Welcome to qnawire.
All right, in this question, we're asked to use the standard reduction potentials found in Appendix E to calculate the equilibrium constant for each of the following reactions at 298 Kelvin. So there's several equations we're going to use for this problem. The first one that we'll need is, I'm just going to put the equations over to the side here. The first equation that we're going to be using is, where am I? Found my pen. Here we go, is that the E cell naught is equal to the potential for the reduction minus the potential for the oxidation. So that's going to give us E cell. Then we need to find delta G. So delta G naught is equal to negative NF, that's Faraday's constant, times E cell. And then from delta G, we can get K, the equilibrium constant, which is going to be equal to E to the negative delta G naught over RT. So for each one of these, we are going to be using all three of those equations. So for the first one, we can see iron is going from Fe to Fe2 plus. It's losing 2 electrons, therefore, this is a 2 electron system, therefore it is being oxidized. Nickel is gaining 2 electrons, again confirming the 2 electron system, and it's being reduced. So when we find the E cell for this, it will be the reduction, so the nickel, which is negative 0.28 volts, minus the oxidation, which is negative 0.44 volts. It's given E cell of positive 0.16 volts. We then solve for delta G, again using the equation to the side. So that's negative, and then we have, this is a two electron system, so 2 moles of electrons, times Faraday's constant, which is 96,485, and that's joules per volt times moles, times the E cell, which we just calculated, which is the 0.116 volts. And we're going to get that delta G equals negative 30875. I'm not going to worry about sig figs right now because this number is going to go on to be used to find K. And finally, K is going to be equal to E to the negative delta G. So that's to the negative 30875 joules, divided by, and then we have R, which is the 8.314 joules per mole Kelvin, times the temperature of 298 Kelvin. We plug all that into the calculator and we find that the equilibrium constant for this first one is going to be, and they're rounding it to 1 sig fig in the answer key, it's going to be 3 times 10 to the 5th. For our next one, we've got cobalt here, and it's going from cobalt to cobalt 2 plus. So again, that is a 2 electron system, and the cobalt is being oxidized. Hydrogen is going from positive oxidation number +1 to 0. Therefore, it is gaining electrons. Therefore, it is being reduced. And again, there's two hydrogens here, each gaining 1 electron, so that is another 2 electron system. So it looks like we have 2 electrons in this case. So again, I'm going to start by finding E cell. So E cell will be the potential for the reduction, which is the hydrogen. So that's our 0. Remember, the reduction potential for hydrogen, since it's what everything else is compared to, is 0, minus that of the cobalt, which is negative 0.28 volts. So we get that this is going to be positive 0.28 volts. So now we can find delta G naught. And delta G naught is going to be equal to negative, and then the number of moles of electrons, which again in this case was 2 moles of electrons, times Faraday's constant, which is the 96,485 joules per volt moles, times the voltage, which was 0.28 volts. And I get my delta G in this case equal to negative, and that's 54,032 joules. So I plug that into my equation for K. So K equals E to the negative 5,432 joules divided by 8.314 joules per mole Kelvin times the 298 Kelvin. And that gives me a K equal to 3 times 10 to the 9th. Finally, for part C, okay, so we have bromine going from Br minus, so as a -1 oxidation number, to Br, which has a 0 oxidation number. So it's losing electrons, so it's being oxidized, and there's 10 bromine, each one losing 1 electron. So this looks to me to be a 10 electron system. Let's double check with our reduction. So our reduction here is the permanganate is changing oxidation numbers from, and if you solved for the oxidation number here, you would find it's +7. It's going to +2. That's 5 electrons that it's gaining, but there's 2 of them. So again, that is a 10 electron system. So we start by finding our E cell. Our cell potential is going to be the reduction, which is the permanganate. So that's 1.51 volts minus the bromine, which is 1.07 volts, to give us 0.44 volts. We then solve for delta G naught, which is equal to negative, in this case it's at 10 moles of electrons, times Faraday's constant of 96,485 joules per mole Kelvin, times the cell potential of 0.44 volts. And I get that delta G in this case is 424,534 joules. So 424,534 joules. So I'm going to plug that into my equation for K. So K is equal to E to the negative, oh, no, excuse me, that was a negative here. So E to the negative 424,534 joules per 8.314 joules per mole Kelvin times the temperature of 298 Kelvin. And plug that all into the calculator, and you get K is equal to 3 times 10 to the 74th. Very big K.